Welcome to the last lecture in this course, Explainable Machine Learning, and today we will talk about interpretation by backward propagation and concept discovery. And as always, I want to first repeat the categorization, and I want to tell you which kind of algorithms we are looking into today. And so first of all, we can categorize by specificity. And you might remember, hopefully, that you can, you have one category which explains the output by the input. These are model agnostic approaches. They are applied post hoc, so it's independent of the model. But then there are these model specific approaches. So you need to go into the model, you need to understand what's going on, you work with the elements, and so you want to understand the mapping. That means what will happen to the output when we change the input. But today we will talk about such approaches where we have a look, or where we need the backpropagation process. So we work with different elements of the backpropagation process. And so let's go a little bit more into detail. So what you see here is again our whale example. So you want to understand which part in the image is responsible for a specific decision. Our specific decision is a specific ID. And so now we have a look at the backpropagation process. So you start from the output and you go back to the input. And the backpropagation path is performed. What is happening in there? We will have a look at the partial derivatives, but then there are also deconvolutions or unpooling, especially in convolutional neural networks, and we will have a look at relevances. So I will tell about this in a few minutes. But let's first have a look into gradient-based saliency maps. So gradient-based saliency maps are one of the first pixel attribution approaches, and it's quite simple if you already know backpropagation. So what you can see here is the equation we use for this approach, and this is nothing else than the gradient of the output with respect to a multidimensional pixel x. So x is the multidimensional pixel. B are the channels. For example, in the multispectral image, you have RGB, near-infrared, or shortwave infrared pixels, or just RGB. In standard images you take with your phone, for example. And LQ here is an arbitrary norm, for example, the maximum norm. And so the partial derivatives are obtained efficiently by running the backpropagation algorithm throughout the multiple layers of the whole network. So here you go back. And I do not want to repeat the backpropagation algorithm. There are a lot of really good explanation courses, even on YouTube, in books. Just look it up if you cannot remember. And if you do this, if you do the whole process, the whole equation for all pixels, this gives us a map of the size of the input with negative and positive values. And in general, this method tells us whether a change in the pixel would result in a change of if a change in the input image results in a change of the output, but by using gradients. So similar to what you heard before, but now we use gradients. And the interpretation of the gradient-based attribution is the larger the absolute value of the gradient, the stronger the effect of a change of this pixel. Or the magnitude of the derivative indicates which pixel needs to be changed the least to affect the output the most. Okay, so this is one very simple method, and it builds the basis for a lot of more sophisticated approaches, or approaches which were developed afterwards. And a method which was specifically designed for convolutional neural networks is called class activation maps, or short CAM. The goal of CAM is to indicate the discriminative regions used by CNNs for classification. So what you see here is such a typical convolutional neural network, but you will see it's somehow needs to be specifically designed for this. So what you have is you have some convolutional layers here, then you have a flattening layer, and then you have a fully connected layer, and you perform a decision in a decision layer. And the output, you have the classes, or just in this case, the whale ID. So the decision layer, for example, is a softmax layer, or in our example of the whales, we used the sigmoid layer, which was more convenient, for example, to see when a whale was not in the database, or it's not in one of these ID, so all scores were just small. So what is done then for CAM, so what is actually happening there? So when we want to compute class activation maps, we replace the fully connected layer with a global average pooling layer. So this part, when you go back here, so this part here is actually replaced by global average pooling layer. Global average pooling is simple, simply averages the activations of each activation map and concatenates these averages and outputs them as a vector. So this is, for example, here you can see the different colors, and then a global average pooling is performed. So we have one value then, and so the color of the layer and the output of the global average pooling is assigned to each other. And then we have a weighted sum of the vector, and this is fed to define a softmax or sigmoid loss layer. So this is, you can see here. What you have here are the parameters W, and these are the weights from the connection between the global average pooling outputs to the decision layer, so it's fully connected. And then what you actually want to have is this class activation map, or this final saliency map. This is done by multiplying these weights with the activation maps. And then there is an extension, because, as I said before, this is quite restrictive, because you need a specific design of the network. So you need this specific part so that you actually get the weights here. And so there was a development of an extension, and this is called gradient weighted class activation maps. And here also same principle, the activation maps are multiplied by some weights, but the weights are now based on the gradients. And it's a more versatile, as I said, since it produces visual explanations for any arbitrary convolutional neural network. So again, we look at the network with multiple layers. So you decide on some layer with convolutions, and we want to analyze the last convolutional layer. This is generally a very good idea, because in the last convolutional layer you have the most complex information. If you remember, when you go through the network, what was said in one of the first lectures, in the beginning you extract mainly edges, and in the end you have very complex features. And of course you can also analyze the edges, but this will not give you really information in the saliency map. So what you do is you have a look at the last layers. So that's what we do here. We have a look at the last convolutional layers here, and then we perform several steps. First step is you perform a forward propagation. So you forward propagate the input image through the CNN, and you obtain a raw score for the class of the interest before applying a softmax or a sigmoid function. And then you set all scores except the one you're interested in to 0. So when we look at our classes here, you pick one specific class, a specific whale ID in our case, and you do not take the final score, but you go a little bit before. You take the raw score, and all the rest of the scores you set to 0 because you're only interested in a specific class. And yeah, this is what is actually performed here. So this X is the input image, and this Fk is this F is your the whole network. Okay, step 2 is now you backpropagate the gradient of the raw score of a specific whale ID to the convolutional layer you're interested in. So that means you start here and you go back until this convolutional layer, and you perform standard backpropagation rules. So you have the gradients, and this is actually what is happening in this part here. Again, if you cannot remember how backpropagation works, have a look at it. But for now, just imagine you go back and you have specific gradients you work with. And step 3 is now you perform a global average pooling. That means the gradients are averaged across the whole activation map, and the importance of each activation map or you get the importance of each activation map for the target class by this global average pooling, and this is exactly what is happening here. So and step 4 is you average all activation maps weighted by their importance. And so what you actually can imagine here is, or you saw this equation more or less before. So what you have here, these activation maps, and then you have this is the weight. And so you have a weighted average of your activation maps. And then there's one crucial part, the ReLU function. The reason of why a Grad-CAM uses ReLU is it wants to remove all the negative values with the argument that we are only interested in the parts that contributes to the selected class C and not to the other classes. Because this has also some practical reasons, because it's sometimes a little bit complicated to interpret what is actually or how to interpret when if something contributes to the other classes. So for visualization, again, you scale the values to the interval between 0 and 1, otherwise a little bit tricky, unless you need somehow to understand also the magnitude, then you do not do this, but for visualization purposes, that's a good way to do it. And then you upscale the image and overlay it with the original image. And this is actually one thing you need to know about the Grad-CAM, because you work in this convolutional layers, and this is quite small, so it's not of the size of the input image. And that's why when you upscale it, Grad-CAM and also CAM tend to be very blobby, because you only can Even if you have here a very detailed activation map, due to the upscaling and because these activation maps are quite small, it very often you get only a rough estimate on which parts in the image are responsible for a specific decision. Yeah, and also I want to mention it again, this procedure is recommended for the last convolutional layer because it will give the most high-level information. So let's have a look again at our whale example. So the task was you have a lot of images of whales, and you want to identify, you want to classify a specific image into a specific whale ID. And the research question you can ask now in the context of explainable machine learning is, why does the network identify images as the same whale or as different whales? And is a whale expert actually looking at the same parts in the image as a neural network? And this is illustrated here again. So you have one image and you have a whale ID, and you want to know where does the network look at? What is important in the image? And here you can see results and comparisons. So occlusion sensitivity map, this is something I already showed you before. These are the original images. Occlusion sensitivity maps, you see they identified the wave flukes, the fluke tips as an important part to it, and identify this for images of the same whale as really the same whale. And this is Grad-CAM. And what you can see is, so Grad-CAM points to one specific part in the image, which is this small notch. And so it's somehow points to the same area as the occlusion sensitivity maps, but the features which are identified as important are different. If you analyze different convolutional layers with Grad-CAM, you might come up with even more similar features than occlusion sensitivity maps, but we only looked at the last one, a specific part, and this gives us the small notch. So it's always worth to not only use the last convolutional layer, but to have a look into more layers and actually understand what's going on, and maybe there are even more hidden features in there which are interesting to analyze. Okay, so let's come to a different concept. So now we do not work with gradients, but with so-called relevances. And for this, there is a quite well-known algorithm called layer-wise relevance propagation. And layer-wise relevance propagation has the goal to determine the contribution of pixels to the overall score by propagating back the prediction of the network, but now with a decomposition. So you decompose into pixel-wise relevances. So again, you use the concept of back propagation, but not with gradients, but now with relevances. And illustrated here is the concept of relevances. So the main idea is you have relevances of pixels, and here in the network you have relevances of learned features, and in the end you have the relevance of a classifier output, which is your raw score. So you know this, and somehow if you go back, you decompose the final relevance back through the network until you reach the input, and then you have the relevance of each pixel. So this is the main idea behind it. So let's dive a little bit more into detail into it. First, into the main concept. So generally, as I said, the method assumes that the classified can be decomposed into several layers of computations. And so first, what we have is you have a forward path, and then you have a backward path, while we decompose the relevances. What we want to know is we want to know the relevance of each pixel for a specific outcome. So that's what I showed before on the last slide. What we already know, what we have, is if the relevance R of the output, and this is the raw score before define a softmax or sigmoid layer. So we start from there, and we use this equation here. We use this equation iteratively to calculate R for every neuron of the previous layer. So actually what you want to know is for each neuron the relevance. So when you go back, it's decomposed more and more and more, so that you end up with a relevance for each input pixels. So what you can see here, so L are the layers. L plus 1 is here the last layer, and L is the previous layer. J is the index of the neurons in the last layer, and in this case we are only interested in one specific class, one specific output. And I is the index of all neurons in the previous layer. So what does this equation actually mean? So what we have here is Z. So Z for now is nothing specific. It generally represents how much a neuron I in the previous layer contributed to make a neuron J relevant. So this, the set of a specific neuron is divided by the set of all neurons in this layer here. And this set depends on in general, the set depends on the use functions in the network, and with this, the propagation rules. So this is the very general main equation behind layer-wise relevance propagation, and then there are a lot of different specific techniques how you can actually use this. So let's be a little bit more specific. Let's have a look at specific network where each convolutional layer is followed by a ReLU rectifier. A ReLU activation function. So A here, the A denotes the activation of a neuron I in the layer L, and here this W, and this W is the weight between the two neurons I and J. So again, what does this equation mean? So let's have a look now at the specific rule, a layer-wise relevance propagation, is LRP0 rule. So now for each neuron J in the layer L plus 1, in this case our output layer, we calculate the influence of a neuron I onto neuron J times the relevance of the neuron J. And this fraction here, this fraction can be seen as the amount to which a neuron I influences another neuron. And this is divided by the sum of all the influences. So one of the most basic propagation rule, or when you use this in this context, and then it's called the LRP0 rule. So, I mean, it seems complicated, but as I said, the general concept is you go back and you decompose all the relevances, and it depends, of course, how which activations you have in the network. And what you want to determine is how the neurons influence each other to calculate the relevances back to the input image. If you are interested in more of these decomposition relevance computation rules, you can have a look, but this is the most simplest one, and you work here with the activations. So to sum up, now I mentioned a few of the most basic forms of algorithms where you use backpropagation rules. The good thing is it's easy to understand and based on well-known concepts. So backpropagation is well-known, it works, and it's understood. And so the thing is, once you understood the main concept, the interpretations, or you know a lot of, or you can, so when you know the basic concept, you already most of a lot of methods which are out there who use this main rule. So the interpretation by backpropagation is flexible regarding what is analyzed. This is good, so you can, for example, analyze single CNN filters or some other activations or specific layers in the network. Maybe you are more interested in not the higher level information, but maybe more in the middle or in the beginning. But there are also something you need to be aware of. So saliency maps can be misleading since they might not only point to the object but also to the surrounding, which is understandable. When you think of animals, for example, specific animals appear in different environments. So the environment might be very important to identify the specific animal in the image. And this is important if you work in the area of remote sensing or similar areas. They work best for images, or the saliency mapping techniques work best for images with a clear foreground-background separation. So if you have a clear object in an image. Otherwise it gets a little bit tricky, so you need to be careful which method you use. And gradient-based method can be quite noisy, since small changes in the input can cause sudden jumps in the gradients. So it depends also a bit on how the computation is done and which activations you use in the network, but yeah, it can sometimes lead to sudden jumps, and therefore, if you have sudden jumps, you have the result is quite some noise in the saliency maps. Okay, so let's go to the second part of the lecture, which is about concept discovery. So far we have spoken about many methods to explain black box models through feature and pixel attribution. I was especially in the first few lectures. But there are some limitations. So first, features are not necessarily user-friendly in terms of interpretability. This is what I said before. You need to be careful what you can actually read from the obtained saliency maps. So they can be quite difficult to understand. So for example, interpretation of a single pixel in an image is usually hard to understand on its own. But this is what saliency maps provide you with. Second, the interpretation itself is restricted to the given features or pixels. So therefore, another approach to overcome all these shortcomings, there's another approach called concept discovery or interpretation with concepts. And the concept can be any abstractions. For example, what you see here is you have color concepts, you have structures or patterns. So you have here, for example, concept of lines, of waves, of dots, or it can even be objects. So you have a sheep concept, a person concept, or a balloon concept. Everything what you can think of with any semantic meaning behind it can be a concept. And I want to show you now two approaches. One is TCAV, testing with concept activation vectors, and activation space occlusion sensitivity. So let's come first to TCAV. So TCAV means testing with concept activation vectors. It's quite famous. There are already also some works in the concept in the area of remote sensing. And the goal is to analyze the model behavior by quantifying a concept's influence on a model's prediction for a certain class, even if it was not part of the training. That's an important thing. So this is what is illustrated here. So you have a specific concept, again, or sheep concept. You have your neural network, and what you actually analyze here is the concept's influence on the model's prediction. So, and you might now ask, okay, but why? So what the approach answers is the question how much a concept striped or a concept sheep was important for a prediction of a trained model. So it's what I said before, you're not restricted anymore what you already have in your input image, the pixel values and or the features, but now you can actually come up with, okay, with different concept. And was this concept, which is for you easy to understand, is this actually influencing my decision? And in some application, for some research questions, this can be quite helpful. And what is good is that TCAV describes the relationship between a concept and a class instead of explaining a single prediction. Therefore, it provides a global interpretation for a model's overall behavior. So let's assume we have a classifier for zebras. So you have here a classifier, and your classifier can identify, okay, that's a zebra. And now we want to know what was important to classify them. So why does the network know that's a zebra? And more specifically, we could ask, was a concept of stripes important to the zebra image classifier? So what we want to have in the end is a quantification of the importance. So what you can see here are different stripe concepts. This can, for example, be different images of stripes, where you would say, oh, okay, this is a good representative sample of the concept stripe. So yeah, our network and the zebra classifier, and this is the output class, zebra. And yeah, such concepts are learned and represented by so-called concept activation vectors, short CAV. And so how can we now learn or calculate them? So to calculate the concept activation vector of a specific concept, we need to prepare two data sets. And these two data sets are illustrated here. So what we have is we have a data set or one set of images showing the concept stripes. And then we have another set of images which are random images. And these random images here illustrated as something else like sheep concept, numbers, dots, whatever it is, but not the concept stripes. Yeah, next what we do is we select a hidden layer in the network where we think we get a good representation of the concept that was learned. And this is actually this one. So very often we use such a bottleneck representation because this is also the main idea about this whole bottleneck architecture with encoder and decoder. So you compress all the information you get from your data set and you compress this in such a bottleneck layer. So here you have the most important parts, and in this case we assume also the most important representation of a specific concept. So we use this bottleneck representation here called FL, and so what we do now is we train then a binary classifier that gives us a linear decision boundary, such as a, for example here, in this case, such a linear decision boundary as we learn from a linear classifier or a support vector machine, whatever you think is helpful here, or logistic regression. And the vector that describes the decision hyperplane is Q CL, this here. So this is the vector standing orthogonal on this decision linear decision hyperplane, decision boundary. And so C is the index for the concept, and L is the index for the layer we used from where we used the representation. And this is exactly the concept activation vector, so this one here. But now we want to test if a specific image, like our one image of our zebra, aligns with the stripe concept. And for this we need a second part, not only the bottleneck representation, but we need a second part, which is the function h to get from this representation in the bottleneck layer to the logics. And this is exactly here to illustrate its h. So h is the function coming from this bottleneck representation to the final logics. So the raw class scores. So HL like is the derive is you can see as the function to derive the output of the whole classifier starting from this representation here. And what we also need are gradients. So you realize today we talk a lot about gradients. Gradients are really helpful. So what we specifically need now are directional derivatives. And as the name says, here we talk about directions. And to quantify whether a certain image X, that means a certain image of a zebra, aligns with a certain concept C, that means our stripes, we can measure how sensitive the whole classifier Fx is when the image's latent representation FL, this bottleneck representation, slightly moves along this, this concept QCL. And this is exactly the directional derivative. So this is what we need for the computation. But let's go through it step by step, because here we need a little bit computations and vectors and see how they work together. So what we have is this FIX. So this is the bottleneck representation of an image X. So then what we have here nabla. This is the nabla here. Nabla always indicates some partial derivatives. So this is the vector of the partial derivatives. So overall, this vector is the direction of what would happen to the output if you change the representation. So it's a specific type of gradient. And this vector, so this vector here, is projected to this concept activation vector. And this gives you the so-called conceptual sensitivity. So this is actually the length of the vector. So the sensitivity is a value, and the value is the length of the vector when you project it down to this concept, or the direction of this concept activation vector. And this is not a per feature, metric, unlike in per pixel saliency maps, but a per concept scalar quantity computed on a whole input or a whole set of inputs. Yeah, so I mean, it depends on whether you like to work with vectors or if you want to imagine it in an illustrative way, like I like to have it. But what is important here to remember is you have this concept activation vector, which is a discrimination of your images with your concept, like here, and some other random images. And this concept activation vector, this QCL here, describes uniquely the decision boundary because it's perpendicular on this. And what you then have here is, this is the bottleneck representation, this is the directional derivative, and then you have this vector here and you project it down to your concept activation vector, and this is the equation here when you project it, and this gives you the conceptual sensitivity. And what you can also imagine imagine what happens if you have a concept activation vector and then you have here this vector standing orthogonal to this, and if you project it down you have 0. So it's not really going in the right in the similar direction. So it's actually not related. And now so we have now this conceptual sensitivity, and you compute it for a lot of zebra images. For example, you can use all training images for class K, which is in this case the zebra class, and we count how often the conceptual sensitivity is larger than 0. So how often does this our zebra images fall into a similar direction like the stripes concept, and then divide by the total number of the tested images. This is what you can see here. So this this notation here means it's the number of images you tested. And yeah, the magnitude is not included in this equation, but of course you can, it could be, we just tested if it's larger than 0 and to get an impression if this really, if the zebra and stripe concept belongs to each other. So let's go a little bit again through the whole procedure. So what you do first is you collect several random data sets. So like sheep or dots or something else, not zebra or not stripe, sorry. And then you learn concept activation vectors from a random data set and a fixed concept data set. And you calculate the TCAV scores from the given data sets. And then you apply, for example, a two-sided t-test, a statistical test, from hypothesis testing theory to TCAV scores against other TCAV scores generated by random concept activation vector, and the random concept activation can be obtained by choosing the random data set as the concept data set. Okay, so this is the whole procedure, the testing. So it comprises the concept activation computation and the testing. So what are the advantages and disadvantages now about this? So first of all, collecting data or collecting some data describing concepts is intuitive and does not require machine learning expertise. That's good. But and also the interpretations are intuitive and can be used to identify flaws. But of course, there are also you need to be aware of some shortcomings. So for example, the used representation should disentangle concept. So the bottleneck layer, we assume that the concepts there, the representation there is able to disentangle this concept. It's sad, or it's already well known that the deep representation are more suitable for this, but of course be careful. If the method does not work, try to use a different representation. And also for some network architectures, it might not be so straightforward because you might not have a bottleneck representation. And also the concepts should not be too abstract. This is one thing, and concepts need to be known. This is actually one crucial part, and I want to talk about it in the last part of the lecture a bit more. What if the concepts are not known? I mean, now we assume we have a concept stripes and we want to test against the zebra, or you want to test zebra against stripes. But what if we do not know concepts? There is a whole research area where you want to identify a concept, or you search for concept, and this research area is called concept discovery. And one application I want to show you here, you already know it from the last lectures, is the detection of wilderness characteristics, because wilderness is not well defined, but what you can do is you can search for concepts. So what is actually a concept of wilderness, and these concepts can help you to get to a more technical definition of the wilderness characteristics. And what we did for this is we collected Sentinel-2 images, and we thought about, okay, what are some areas which describe wilderness, which show wilderness, and which not, what kind of areas do not show wilderness. And we came up with two classes, anthropogenic and protected areas. So protected areas, they are not so much human influence, in the best case no human influence, and here you would say yes, these images somehow should contain wilderness characteristics and some concepts, semantic concepts, and these anthropogenic images here, and this is the perfect counterexample of wilderness characteristics. So it should contain other concepts, not wilderness concepts. And we collected images from whole Fennoscandia for this, and so a lot of these images, and then we designed a network. So illustrated here is the network to actually derive a wilderness score. And what we do is I already showed the network in one of the last lectures, but I want to briefly repeat it. So what we did is we have a UNet, so encoder-decoder network, and then we have these activation maps as an output, and based on these activation maps we have a second decision network. And the decision network gives one output, which is a wilderness score. So how much in the image does contain, or how much is the score of this wilderness in the image. So let's dive a little bit more detail into what was actually done then. So we take this middle part, the activation maps from the middle part. So what we used our training samples, Sentinel-2 images, over 19,000 of them. And then we computed for each of these activation maps with 3 channels. That means the output of the first part of the UNet is 3 activation maps, 3 channels. And then we use each pixel in this activation map and put these pixels into a so-called activation space. So each axis here, each axis in this activation space belongs to one activation map. And what you can already see is there's some structure in it. So we already talked about this. Okay, so what we did then is remember what I told you about occlusion sensitivity maps. where you cover up something in the input image, and then you see how much the output change when this part is covered up in comparison to the original image. We use this concept, but now this procedure, we use this procedure now, but in the activation space. So what we did is we defined a cube, and we systematically went through the whole activation space, and we set all activations which fall into this cube to 0. So we went back from the activation space to the activation maps, and all activations which fall into this cube are set to 0, and then we fed back these new covered up activation maps and saw how the score of the output changed. And we did this systematically for the whole activation space, and if you do this, you can get such a connection between the activations and the sensitivity, because when you cover up specific activations, you will get a specific sensitivity, which is the difference between the original score and the score after you occluded this set of activations. And you can already see that there's some systematic behind it. So green are all sensitivities where you say this is sensitive towards wilderness, towards these protected areas. And in purple illustrated are the sensitivities or these activations which are sensitive towards anthropogenic areas, so no wilderness. And if you do this so if you now use the sensitivities, you can use it as some kind of lookup table, because every time you feed in some image to the network, you get activations, and because now you have the connection between specific activations and the sensitivity, you can immediately translate it to such an image you can see here. So here illustrated is one image we did not see before, which was not used in the learning process. And green illustrates patterns identified by the network which are sensitive towards the wilderness. And in pink are regions and patterns sensitive towards non-wilderness, like, for example, what you can see here on the bottom, this area. These are actually artificially created forests. So this seems to be connected to wilderness, but it's not, because it's artificially created, so you have man-made structures in it. And such experiments might help us to understand patterns and processes hidden in our data in a much better way. So, and because we talked about concept discovery, what you can do now is you identified areas, and now you can connect it, for example, to land cover information or some other meta information, or you can go and ask an expert, or maybe you are an expert, and you can look at this image and search for concepts which align with this sensitivity analysis. So that's how you can discover the concepts. And then there's some results you can see here. So, for example, you can also use this to analyze the change on Earth. So, for example, you can see on the bottom two images or the same scene but in different years. And what is hard to see in the regional image can be seen in a much better way in the sensitivity image. So you can see that there's a spread of concepts and of areas which are connected to non-wilderness. And because I already told you, we used the concept of occlusion sensitivity maps, and we compared our results also to input image occlusion sensitivity, where we covered up a small part in the input image. And what you can see here, it's not really working. The reasons are the following. So first of all, you cannot use big images for input image occlusion sensitivity, because if you have a huge image and you cover up a small part, nothing really would change in the output. So you need to divide, your image need to be small enough, but if you do this, you get for each patch a different result, and so that's why you get such artifacts looking, what you can see here. And what you can also see, because it's quite big, it has trouble to really get the concept and right sensitivity out of it. So so the difference between the input image occlusion sensitivity and the activation space occlusion sensitivity is quite large, although the main pattern is there. But still, the activation space occlusion sensitivity looks much more reasonable. Okay, so let's come back to some final, or not, let's come back, some final remarks about the advantages and disadvantages. So the good thing about concept discovery methods is that the concept do not need to be known beforehand. It's fast, since the activation sensitivity relationship can be looked up. So this is what I showed you. So once you have learned the sensitivity space, you have a lookup table. So it's super fast to derive these images. But still, although you have discovered concepts, these concepts might be hard to understand. You still need to somehow make sense of out of the results. So you need an expert or some further additional information like land cover information. And also the concepts might get fuzzy in case the network's accuracy is not high. Okay, with this, this is the end of this lecture and also the course about explainable machine learning. The goal of this whole course was to give you a first impression of what explainable machine learning is and what are the possibilities. So what can you do? And I mentioned a few methods, but the field is super evolving, fast growing at the moment. So nearly every day new methods pop up. So if you are interested, have a look and see what is out there and what you can do with it. And a last sentence is also, so explainable machine learning is not really something new. So it's just get a new possibilities with neural networks, but actually feature importance was already there many years ago. For example, it was used with random forest. And another take-home message is don't forget you need domain experts, because you only get explanation if you have domain knowledge, otherwise you only get interpretation. And with this, thanks a lot. I hope you had fun and you learned a lot, and see you in one of my next courses. Thanks.